Welcome to EPG Pathsala Architecture Lecture Series for MArch students. And in this module, we are going to see the wind energy and small hydro system. And these are the learning objectives, that is the performance analysis of a wind farm, small hydropower, the current scenario, the scale and schematic of SHP, and small hydropower and components and working. And the performance analysis of wind energy system, and it has very important three factors, and through which we can analyze the performance of the wind turbine generator, the technical availability, the real availability and capacity factor. Technical availability is total mission time minus downtime due to grid and machine failure divided by the total mission time. The total mission time is the entire year, 365 days into 24, it is 8,760 hours. Out of this total mission time, and apart from downtime, and what is the total mission from total mission time, when we deduct the downtime of due grid and machine, and that ratio will be the technical availability, that is total mission time minus of downtime due to grid and machine failures divided by the total mission time. And the real availability, and the machine may be available, and if there is no proper wind velocity, it cannot generate power, that is real availability, total mission time minus downtime due to grid, machine and low wind divided by total mission time. So, that is real availability. So, technical availability will be high in the order of 95% plus, real availability may be in the order of 80% plus. Capacity factor, that is like efficiency factor, energy generated per year in units kilowatt hour divided by turbine rated power into number of turbine, number of hours per year. This ratio will give you the capacity factor. And this is about the performance analysis, monthly average wind power density in Muppandal wind farm. Muppandal is the very good site in the country, maybe even in the world. Second best site, first site is California, next site is Muppandal area, which is in southern part of Tamil Nadu. And this graph represents the wind power density, watt per square meter. And so here, so from the month of April to March, it is given, and so from May, June, July till August, the wind power density is quite good. That is it is in watt per square meter. And in the November, December, January, February, so here it is quite low even till March, and because of low wind. And so this from May to August, it is quite good in Tamil Nadu weather condition, and particularly the Muppandal meteorological data represents this kind of performance. It is always better from May to August. After that, it could not generate much because of the less wind velocity in that region. And this is about the power generation of wind farm, generation in units it is given, and for 4 years, for 5 years it is data was collected, and this particular year it is quite low because of much failures in the wind turbine, and from here it is steady, not much failures. And initially it was good, and here because of much failures, it is low, and after that it is quite steady. And this is about comparison of technical availability, real availability and capacity factor for the wind farm. And here this is the technical availability, real availability and capacity factor, and over the years it is quite good, about 95% plus. Real availability is also quite good, 80% plus, and capacity factor is about 25% plus. And average technical availability in that particular Muppandal area, it is 98.26 percentage. Average real availability is 83.06 percentage. Average capacity factor is 26.61 percentage. And this seems to be good site, and this is the comparison of various availability and capacity factor. And again, this is a percentage distribution of stoppage. Average stoppage due to grid, it is about 13 percentage. Here because of low wind, this is the stoppage time. That means the wind turbine did not function, 78.55% because of the low wind. And we cannot help it, of course, we cannot do anything with this, but then these failures could be minimized. The grid 13.19, it is in our hand when we maintain the grid properly, and definitely this could be avoided. And mechanical failure like components failure 5.2%, this could be avoided. And electrical components failure 2.02, it could be avoided, and control panels 0.27, and these we can attack and we can bring down these failures, and so that the stoppage time can be minimized. And these are the causes of wind failure: grid outages and substation maintenance, meter relay testing and breaker fault, overload, line problem, feeder tripping, power evacuation problem. These are all various grid failures, and it has to be minimized, and it needs preventive maintenance so that it could be avoided. And of course, in southern part of India, we have very poor grid lines, and it needs separate corridor to evacuate the electricity generated from wind farms to the other parts of the country. And this is the frequency of the failure. So, average mechanical stoppage 5.2 percentage, average electrical stoppage 2.02 percentage, average control panel stoppage less than 1 percentage. Again, all these could be minimized. And by better service, but with good maintenance, and when we maintain good quality, definitely this could be minimized. And these are all number of failures much here and here, and maybe the mechanical component failures. And here the figure shows percentage of failures over the 5 years of operation, and the failure due to mechanical components, it is about 67%, and electrical and electronic components about 33%. More number of yaw unit failures and hydraulic unit failures. Here when you look at the failures distribution, hydraulic unit, because very frequently the brake is applied, that is the maximum, then followed by yaw unit, because the wind direction keeps on changing, it has to be operated, and then the blade failure, gearbox failure, and other failures, brake pad failure. These are all various failures happened in the wind farm at Muppandal area. And so here one problem could be solved. Maybe a company requires this much units of electricity, that is 1 crore and 5 lakh and 15 crore, like it is in millions. So, this much units of electricity, and it needs, the company needs, but what kind of wind farms they can go for. what would be the capacity they need. So, that can be solved based on the previous performance analysis examples. Maybe with the technical availability, we can assume it is about 30%, and the required power, that is it is in the that is the power generation requirement, and underneath we can have the capacity of the machine and number of machines, etc., and we can identify what would be the capacity of the machine and how many wind turbines are necessary and how much area is required, and everything can be analyzed based on the previous performance analysis. And here, so after the wind energy system, and we are going to see briefly about small hydro. Small hydro, it is coming under renewable energy sources, and the major hydro, it is called conventional power plants, which has high capacity 500 megawatt, 600 megawatt, 300 megawatt. It is being installed across the country, across the rivers, and it is there for many decades. It generates electricity whenever the dam is full, and apart from it, this concept is recently introduced, small hydro, and this kind of hydro energy can be generated across the streams in the Himalayan region, or wherever there is small streams. Across that we can have a small reservoir and we can generate electricity out of it. This is small hydro. And small hydro, and so far we have installed 4,323.35 megawatt of electricity. It is huge, and yeah, the power generation 8.33 billion units we have generated through small hydro power. And small hydro power potential that is about 15,000 megawatt we have it, and identified potential that is about 14,294 megawatt, and we have about 5,403 sites. Installed capacity of 2,108 megawatt, we have about 618 projects. Under implementation 698 megawatt, we have about 226 projects. And this is about hydro driven by solar power, and from solar energy, and because of solar's heat, the water gets evaporated, and then the cloud is formed, and then it gets condensed, and then the rain drops on the earth, and it is stored in the reservoir, and then we generate electricity out of it. And this is the worldwide classification of small hydro power, and so in India, when it is lesser than 25 megawatt capacity, then it is coming under small hydro power, and it varies country to country, and if it is UK, even if it is less than 5 megawatt, then they call it is small hydro, and Sweden, if it is less than 15 megawatt, they consider it as small hydro. Colombia, if it is less than 20 megawatt, then they consider it as small hydro. Australia, less than 20 megawatt. China, less than 25 megawatt, and Philippines, less than 50 megawatt. New Zealand, less than 50 megawatt. But overall, if it is less than 50 megawatt capacity, then it is coming under small hydro, and if it is above 50 megawatt capacity, then it becomes medium or major hydropower plants. And the large hydro, more than 100 megawatt, feeding into a large electricity grid like Mettur Dam or Krishnaraj Sagar Dam, and which has high capacity, and it feeds into a large electricity grid. Medium hydro, that is 15 to 100 megawatt, usually feeds feeding a grid. Small hydro 1 to 15 megawatt, usually feeding into the grid. Mini hydro above 100 kilowatt but below 1 megawatt, either standalone schemes or more often feeding into the grid. These are the various type of hydropower projects. And micro hydro from 5 kilowatt up to 100 kilowatt usually provided power for a small community or rural industry in remote areas away from the grid. This is micro hydro. And pico hydro from a few hundred watts up to 5 kilowatt and remote areas away from the grid it is being located. And these are the typical types of hydroelectric installations, and this is the low head and this is the medium head and this is the high head, and here this is the reservoir, small reservoir. The water is stored here in this reservoir. This is the barrage and this is the turbine is kept here, Francis turbine or Kaplan turbine. And in the small reservoir, when the barrage is opened, the water will gush out through the turbine blades, and then it is connected to the generator, and the kinetic energy, the potential energy is converted into mechanical energy. Again it is converted into electrical energy. Then the water is going through the tail head, this is called tail head, and it goes for the agricultural purposes. The medium head, the dam height is little bit higher when compared with low head dams. This is a medium head dams and this is a reservoir, and it has penstock, and through the big pipeline the water will be coming and it is gushing out through the turbine, and here there is the hydraulic turbine. Because of the high pressure and velocity of the water, and it will impinge the blades, and the blades will rotate and it generates mechanical power, and it is connected to the generator, it converts into electric power, and the water goes out through the tail stalk. This is about the medium head, and this is the high head, huge reservoir and big dam, and the water is stored here, and through the long penstock it is coming down with a very high pressure and velocity. It enters into the hydraulic turbine which generates mechanical power, and again it is converted into electric power through the generator, and then it goes via tail stalk for the agricultural purposes. These are the various types of hydroelectric power. And this is small hydropower site, and this is the powerhouse, and this is the penstock and small reservoir, and this is the small river or stream, and it is built across the river and stream, and small hydropower is generated from this. And the turbines are turned by water. Because of the water force, the turbines are rotating. That turning motion drives a generator which produces electricity. The mechanical power is converted into electricity. Two things to make power, the head and flow. And this is about small hydropower components. And here these are the transmission line. After the power generation, the power is distributed through the transmission line. This is the dam storage to store the water, and this is the long penstock, and through which the water is gushing out, and it enters into the turbine blades. And this is a generator, and it generates electricity. And this is a turbine, maybe various turbines are used in the hydraulic turbine to generate the electricity. And these are the major components of small hydropower. And how a small hydropower plant works. Flowing water is directed at a turbine. Remember, turbines are just advanced water wheels. The flowing water causes the turbine to rotate, converting the water's kinetic energy into mechanical energy. The mechanical energy produced by the turbine is converted into electrical energy using a turbine generator. Inside the generator, the shaft of the turbine spins a magnetic inside coils of copper wire. It is a fact of nature that moving a magnet near a conductor causes an electric current. And these are the various hydroelectric turbines, classification of turbines. This is an impulse and reaction turbine, major classification, impulse turbine and reaction turbine. Under impulse, the Pelton wheel and Turgot wheel and cross flow, and from the reaction turbine, Francis turbine and axial flow, we have propeller and couple-on turbines. Power equation of hydro: the water is fed from stream or canal to the turbine by a closed pipe, that is penstock, through diversion works. The turbine in turn rotates the generator for electricity generation. The power in kilowatt, it can be calculated by this gravity 9.81 into discharge cubic meter per second into head, the meters, and efficiency. And it has some advantages and disadvantages. Positive, that is advantage, no emission, the hydropower, and it is mature technology. It is renewable. Whenever the rain comes and it gets stored in the reservoir, and from there we can generate electricity with a high efficiency of 80%, long life 40 to 50 years, low maintenance cost, skilled work, and change using area. So, these are all positive aspects. There are some negative aspects, that is social impacts will be there, high initial capital cost necessary, impacts on river flows and aquatic ecology, and variable output dependent on rainfall and snowfall. If there is no rainfall, then we can't have storage, and then we cannot generate electricity. And if it is snowfall, if the reservoir is frozen, then we cannot operate it. And high cost of dismission and bureaucracy. So, these are all negative aspects. Yeah, in this section, and we have seen mainly the performance of the wind turbine generator, how to analyze the performance of wind turbine generators, particularly how to calculate the technical availability, real availability, and capacity factor. And machine may be technically available, but if the wind velocity is low, it cannot generate electricity, that is the real availability. And capacity factor, though the Betz limit is 59.3, practically if we even achieve 40%, it is very remarkable. And so, the downtime has to be minimized. The frequency of failures have to be avoided by proper maintenance, by proper inventory, having adequate components, and somehow we can rectify the mechanical failures, electrical component failures, and sensors failures. By avoiding all these things, definitely we can improve the performance. With the low wind, we cannot generate electricity. So, it is not in our hand, but then and the machine component failures, electrical component failures, and sensor failures, these are all could be avoided. And though it faces any failure, immediately the components have to be replaced. And so, in this module, and we could see the various parameters and how to analyze the performance and what are the advantages and disadvantages and everything we have seen about on wind energy. And next we discussed about the hydro, that is small hydro. In the small hydro, and whichever it is less than 25 megawatt, it is coming under small hydro. And in that we have a lot of potentials across the rivers, across the streams, and we can have some storage there, and we can make a small reservoir, and we can have the mini hydraulic turbine capacity of 25 megawatt or 50 megawatt maximum. We can have it according to the capacity, we can have from 5 megawatt to 25 megawatt, and we can allow the water through the penstock, and we can activate the turbine, and then it can be coupled with the generator, it generates electricity. And the small hydro, we have good amount of potential, and across the country it has to be identified, and we have to bring much more small hydro power, and it could be tapped, and then the electricity could be fed through the grid, and again it is clean energy. It has lot of positive aspects. It is clean, it is renewable, and need not pay for the fuel, and it has very good positive aspects. Of course, it has some little negative aspects. Of course, it is slightly expensive, and if there is no proper monsoon, we cannot generate electricity, and it depends upon the rainfall in the country. And somehow, and we could see where to be installed, where are the potentials available. We have to identify, and we have to invest, and then we have to generate electricity, and the lifespan is very good, about 50 years it will work once it is built, and it is having long life, and when compared with other renewable energy based power plants, it has very good long life, and definitely our electricity demand could be met even with small hydro. Thank you.